Hello, welcome my fanatical physics students. This time what we're going to do, I'm going to teach you a little bit about relative velocity. Relative velocity comes into play a lot because oftentimes you don't have just one velocity you're dealing with. If you're in a car and you're throwing a ball up in the air, you throw that ball up in the air and you catch it. Well, how fast is that ball actually moving? It's moving the same speed as your car is. So to somebody on the ground, if you were to throw that ball to them, if they were just standing on the sidewalk and you were to throw that ball to them from the moving car, that ball would be going a velocity, away from them that whatever the car is moving, right? In addition to going up. And so it wouldn't really work. But if you're sitting in the car, you can throw the ball up and down and catch it because you and the ball are both moving in that same velocity. So the ball relative to you doesn't have a velocity like, say in this direction. But if you were to throw it to somebody on the ground, the ball would then have a velocity in that direction. So relative velocities come into play a lot. For example, let's say that a wagon is moving down the street and is moving down the street at 0.75 meters per second. And let's say that there's a little caterpillar on there, and the caterpillar is walking backwards at 2.0 centimeters per second. Okay, so that caterpillar relative to the ground isn't going the full 0.75 meters per second because it's walking, if it's going that way, it's walking backwards. So all you'd have to do is subtract it. So it's going to be 0.020 meters per second. We'll convert centimeters per second to meters per second. So that equals 0.73 meters per second relative to the ground. So we'd say in the positive direction relative to the ground is what the caterpillar is moving because he's going away from. Same thing would be true if you're walking on a bus. So say that this is a bus and there's the front of the bus and there's windows. And right, so let's say that the bus is moving at 10 meters per second. If you are, here you are, woo, hi. If you're walking to the back of the bus at 0.5 meters per second, that means relative to the ground, right? Relative to the ground, you're only going 9.5 meters per second because you're walking backwards, which is actually subtracting from this forward motion that the bus is going. So stuff like this comes up. Let's go ahead and do kind of a more complex problem right here. Let's think about an airplane. So let's say we've got an airplane, and I'm going to draw an airplane. Ooh, there it goes. That is a sweet airplane. All right, so let's say that airplane is flying along. And let's say that it needs to continue flying along in this direction. Let's say that the airplane can go 285 kilometers per hour, and that's the speed that it wants to. That's the speed that it is going relative to the air. So this is to the air, right? And let's say that it needs to continue going in this direction. Let's say that this direction is north, right? Which would make this direction east, this direction west. And nope, south. Sorry, south, and then this would be west. Okay, so here's my coordinate right here. So if you're down here on the ground, here you are. Woo! Say hi, airplane. So this is going to be going 285. Now let's say that there's a wind. Let's say that there's a wind that comes up, and that wind is blowing on the airplane. And it's blowing in this direction, and let's say that it's blowing 30 degrees north of east. So 30 degrees north of east. So so if this is our coordinate plane, this is going to be east. Let's say we got 30 degrees right here, right? And so what is that going to do to the airplane? Well, it's going to push it in an east direction. Which is the wrong way. It needs to continue to go in the north direction. And it's also, because it's also going to add to the plane's velocity in the north direction, because that's the north direction right here. So what is the plane going to have to do? Well, that plane is going to have to take its, I'm going to go ahead and get a different color. It's going to have to take its motion, which is you know, or its velocity right here, which is 285 degrees, and it's going to have to angle up slightly to the west, right? So this is the west direction. And how much is it going to have to angle up to the west? Well, it's going to have to angle enough to the west to compensate for that wind pushing it to the east. So what we need to figure out, so if this is our plane can go here 285 kilometers per hour, right? And we know that we're going to have to angle up to the west. We got to figure out how much to the west is it going to angle up. So this is my vector to the west, and it needs to have this vector to the west to cancel out this vector to the east. So let's go ahead and solve for this vector to the east. So I told you that this was, maybe I didn't tell you, but this is 95 kilometers per hour. So let's say that this wind is blowing, and this is really common with an airplane. An airplane constantly has winds it has to adjust for, so it's going to have to angle itself, you know, against the wind essentially. And then a lot of times what airplanes try to do is they try to fly in jet streams where the wind, the most of the wind is pushing them in the direction that they want to go. And in this case, this wind right here is going to help the airplane. It still is going to have to adjust to the west a little bit. So let's go ahead and figure this out. So if this is 95 kilometers, I'm going to go ahead and I want to solve for this side right here, which is the adjacent. So the cosine of 30 times 95 is going to give me 82.3 kilometers per hour. So that means that I need to adjust 82.3 kilometers per hour in the west direction in order to compensate for this wind, which is blowing 82.3 kilometers in the east direction, right? And then I know that whatever this is right here is going to help me out. So this new vector is what I'll end up with in the north direction, right? Right over here. So let's go ahead and figure this out. So once I adjust this up, what I really need to know is I need to know what is this angle right here. Well, this angle right here, this angle theta, we could figure out because we know the hypotenuse and we know the adjacent. So the cosine of this angle, sorry, I don't know what the angle is. The cosine of this angle right here is going to equal the adjacent, which is 82.3 kilometers per hour, right, divided by 285 kilometers per hour. Go ahead and do that, and then I take the inverse cosine, and I'll find that this angle right here actually equals 73 degrees. So 73 degrees is my angle right here. And now I could actually figure out what this new vector is here in the north direction, because that's what I'm going to actually be traveling at, because essentially what I've had to do is take my 285 and angle it away from my direction, which is going to subtract some from my direction in the north. So if I take the sine of 73 equals opposite over hypotenuse, I will discover that my angle is that my new vector here is 270, so it's 273 kilometers per hour, right? So that's now kind of gives me a little bit of direction help. So with my airplane, as long as I angle it 73 degrees, and let's see, what would this angle be? This would be, let's say, west of north, right? So as long as I angle this thing 73 degrees, wait, actually, my 73 degrees was right here, so it wasn't west of north. That was 73 degrees, we could say, is north of west. So 73 degrees north of west. So let's go north of west. All right, so as long as I angle my plane 73 degrees north of west, I'm going to be able to compensate for that wind that's pushing against me to the east, and I will continue going in the north direction. Now, I won't be able to go quite as fast, 273 degrees, but we find out that the wind is also pushing in the north direction as well, because that wind was, remember, 30 degrees north of east. So how much is it going to push me to the north as well? So if I take the sine of 30 times 95, I'll actually figure out what this vector is right here, and it turns out to be 47.5 kilometers per hour. So 47.5 kilometers per hour is the wind is pushing me in the north direction. I don't need to turn against that. So I'm going to let the wind push me in addition to that. Now, relative to the air, this is what I'm going. But since the air is also moving relative to the ground, I would add these two together. So from this guy looking up, the plane is actually going 320 kilometers per hour relative to the ground, which is important. You want to know how fast you are going relative to the ground, because that's going to tell you, where you're, so if this is destinations, tell you how fast you're going to get there. And so oftentimes airplanes will do this. They'll make sure to fly in an area where the wind pushes them in a direction, and they'll often have to adjust against the other direction that they don't want. But as long as they can get some extra help from the wind pushing them in the direction they want, they'll go with it. So hopefully this helps you out. Here's two really important answers right here. This is my speed relative to the ground. This is my speed relative to the air in the north direction. And this is my angle that I'm flying in order to compensate for that wind so that I continue going north.